In the previous video, we were talking about the Alice M1K data logger tool, in which we looked at the discharging of a capacitor, which is essentially an exponential decay. So what we'll do here is we will use Matlab to sketch out the discharge of the capacitor, the voltage waveform for that. And we will also try to import the data that we collected using the data logger tool into Matlab and view that as well. So the first, what I've done here is I've created a new script, and you can do that. If I go to home, you can see this new script option. I've clicked on that, which opened up a new empty editor window for me, in which I can type in a bunch of Matlab commands so that I can run them all at once. So the first command I've written is clear all, which essentially wipes out all the variables that I have currently in my workspace. You can see that I have none right now. CLC clears out my command window, and close all closes all the existing figure windows. I don't have any right now. A percentage is used to start a comment. So the comment that I'm making here is I'm trying to go for equation for discharge of the capacitor. So in my line 5, I've written the time variable. So I've initialized my t, the time variable, to start at 0, go up to 2 seconds in steps of 1 millisecond. 1e minus 3 is 1 millisecond. My resistor that was part of my circuit was 10 kilo ohms, so that's 10e3. The capacitor in my circuit was 220 microfarads, so that is 220e to the negative 6. Tau was the time constant, that's a product of R and C. V in, my supply voltage was at 5, so that's the voltage that the capacitor got charged to. And then I started discharging it when I removed the voltage supply. What I'll do here before I go on is to adjust my R. I know that the voltage was being measured using the voltmeter, and the voltmeter that was available to me on the M1K had the internal resistance of 1 mega ohm. So in fact, my R is not 10 kilo ohms. In reality, it is going to be 10E3 multiplied by 1E6, 1 mega ohm, divided by the sum of those two. So 10E3 plus 1E6. It's going to be close to 10 kilo ohms, but that is what it is precisely, because those two would be in parallel. All right. Tau is RC, V in is 5 volts. And as soon as we removed the 5 volts wire that was charging the capacitor, we saw that it was an exponential decay. And my claim was that it is going to do an exponential decay in this particular equation. Voltage across the capacitor, Vc, is going to equal V in multiplied by e to the negative t over tau. The dot that you see over here is an element-wise operator. So the dot is for V in multiplied by all the elements in e to the negative t over tau. So when you do the divide, so if you put the dot before the operator, it just does a element-wise division or element-wise multiplication here. So that's what I'm finding out, Vc, and then I'm going to plot. On the x-axis, I'm going to plot time variable here. On the y-axis, I want Vc, voltage across the capacitor. Hopefully, I can see an exponential decay. I want that plot to be in red color, and I want the line width of that plot to be 2 instead of 1. So let me see what happens when I run this. So running is right here at the top, or you can simply hit F5 on your keyboard. I'm going to do that, and this particular figure window pops up. So on my x-axis, I have time 0 to 2. On the y-axis, it starts at 5 and then exponentially decays. And I can actually add some data points. So for example, if I turn on the data tips option, I can right click and create a new data tip. I can put it over here, right click, create new data tip, put it over here, and I can actually check whether it is doing the thing that it claims to do, which is an exponential. Create a new data tip right here, and you can you do as many as you want. So that's your perfect exponential decay based on the Matlab equation. So now let us try to look at, so I'm going to close out of this. Now let us try to bring in the data that we collected. I've already put the CSV file in my current folder. That's the file that we recorded. So in order to import that data, what I'm going to say is data equals CSV read. That is the command that is used to read a CSV file. And inside the parentheses, I'm going to type in apostrophe strip, capital STRI, and then if I do tab, it is going to fill in my name because there is only one file and one thing that matches strip and so on. So I can use tab for that. And then instead of bringing in data from the first row, first column, what I'll do is I'll skip the first row because I know the first row is corresponding for time, channel A voltage, channel B voltage. So I don't want that particular row. So I don't want first row. So I'm going to start recording after first row, but I want all the columns. So zero to be skipped. I'll do a semicolon at the end so that all the data doesn't echo back in the command window. And that's going to be my data. So let us see what happens when I run this. I'm going to again see the plot, but I don't need that for now. But if you see my workspace, data has come in 912 data points, and there are 3 columns, one corresponding to time, the second one for channel A, which is what I want, and the third one for channel B. I don't want that. So what I'll do is in a different figure, say figure 2, I will plot the time variable. In this case, it is going to be all the rows of first column. That's my time. And I'm going to sketch something else on the y-axis. I'm going to do data, all the rows, second column. That's channel A. And then close it out. And for this one, I will choose a black color and maybe a line width of 1 will do, which is the default. So let's see what happens now. So if I run this, I have 2 plots that show up. One is the one that we recorded. The left one is the analytical one. That's the perfect one. This is the one that we have recorded. So what we can do in the recorded data is actually zoom in on the data which we could actually use. So for example, if I zoom in on the exponential decay part, that happens just after the 25-second mark, we can see that it is an exponential decay, but it is experimental. So what I'm going to do is create data tips again. So that is going to be at 5, for example. Then I'm going to do another data tip over here. And now I can start to see if this is actually doing the exponential at that rate of negative t over tau. New data tip right here, and so on. In fact, if I subtract 25.29 seconds all the way in my data, then I can clearly see what is going to. So here the x-axis is time, and the y-axis is the voltage. So using a multiple data points, I can find out whether the decay constant matches the one that I expect or not. All right, so I hope you find this demo helpful about how to work with data in Matlab.